All right. Hello, class, and welcome back to part C, or part 3 of this lecture. So in part A, we talked about things that are weird about nonlinear systems. In part B, we talked about the desired properties of nonlinear systems. So properties of the map from initial condition or state to solution, which we define in terms of the solution map. Now we're going to come to the tool that we use to transform, ultimately, these properties, or the condition for these properties, into an LMI. Right? And as for linear systems, the tool that we're going to use is Lyapunov functions. Unlike for linear systems, however, the Lyapunov functions for nonlinear systems are a little bit more complicated. And they prove different things depending on the conditions you impose on them. And we're not going to go through all of the Lyapunov theorems for properties of nonlinear systems. And in fact, we're not even going to go through this one, right? This basic stability theorem right here. We'll just give a brief sort of outline of the proof, and I'll leave it alone. I will give a sort of a more detailed proof in the case of exponential or L2 gain, because that's a somewhat more important one. But we're going to try and keep those proofsmanships to a minimum. In any case, so let's start. So basically, the simplest Lyapunov function or Lyapunov theorem you can give is this one, right? If there exists a function which is positive for every x not equal to 0, and v of 0 equals 0, that's an important one. Kind of make sure that's satisfied. And v dot is less than 0, less than or equal to 0. Notice the less than or equal to, that's important. There. Then the system is stable in the sense of Lyapunov, and I should say Lyapunov stability, right? It proves Lyapunov stability. And furthermore, any sublevel set, and we're going to be talking about sublevel sets to some extent in this course. Sublevel set of the Lyapunov function is a domain of attraction of the origin, meaning it doesn't necessarily actually go to the origin, but it's bounded. So it's Lyapunov stable on that domain. And this is actually a necessary and sufficient condition. Necessary and sufficient. So sufficiency we're going to go over to some extent. Necessity is an interesting point. So if we want to think about necessity, though, there always exists a Lyapunov function which proves these system properties. And this extends to exponential, L2 gain stability, all these properties. There's lots of what we call converse Lyapunov functions, converse Lyapunov theorems. Which we're not going to get into. But they all say more or less the same thing, that if the system satisfies a certain property, then there exists a Lyapunov function which proves it with certain conditions on its derivative. And why is that? Well, okay, so let's go through the basic theorem, right? So this is the basic theorem. So we have a Lyapunov function which is 0 at the origin. It's positive everywhere, and its derivative, and here I should actually mention what is v dot d dt, actually v of x of t. Well, we just apply the chain rule, and that's where we get this term right here. Right. We apply the chain rule. What's the derivative of v with respect to x? Well, there are several x's, so we actually have to form the gradient of v. So that's a vector. And then, so that's delta v, delta x with respect to all those xi's. And then here we have the xi, the derivative of x itself, x dot of t, xi of t here. And that's, of course, just f, the vector field. Okay. So this is the derivative of v. Right? So if that is negative definite in this domain, and it's V is positive in this domain. So here's, say, our domain, D, and if V is positive everywhere in that domain, and it's decreasing everywhere in domain, then every sublevel set of that Lyapunov function, so x such that V of x is less than gamma, is a domain of attraction of the origin. So the basic concept of the proof is that if you start in this set, right, then everywhere in this set, V dot is 0. Or, sorry, V dot is less than 0. And so along trajectories of that solution, right, your V of x of t at any given time is still going to be less than gamma, right? Because it was less than gamma when you started, and because V dot is less than 0, it's going to stay less than gamma for all time, right? So, and then, so we stay in that set, and it's decreasing, and then these conditions here allow us to say that the norm of the system as well it stays in that set, or is bounded in some sense. So there's a couple of parts to this, right? So first of all, we can conclude well-posedness. So the Cauchy problem is satisfied. So the solution map exists. G of x of t exists. And it's locally Lyapunov stable, right? So the solution map is bounded or continuous in that sense. G of x t is bounded. We don't know what by, but it's bounded. That's in some c x. Furthermore, right, if that derivative is strictly decreasing everywhere, not at the origin, then we also can conclude asymptotic stability. So this is a theorem which says if these sort of optimization-like conditions are satisfied, then we can conclude continuity of the system G. And furthermore, we have this additional constraint under which we can get asymptotic stability. Right? So I'm not going to go through the proof because, again, we do the proof in the exponential case, but I'll just give the outline of it here. So for existence, so I actually did that. We show that it stays in gamma. For existence, right, because, right, you prove that any solution stays in this this V of x less than or equal to gamma. Then, right, you can conclude that the solution stays inside that that sublevel set, and because this function is Lipschitz continuous on any compact set, and this set is compact because it's contained in D, we have a solution for some finite fixed time from, say, x of t to x of t plus delta t, right? But then if we initiate the same theorem at that new t plus delta t, because we're still in the sublevel set, we can conclude all the results here still apply, and so we can continue that solution by another delta t. So x plus 2 delta t, sorry, you can't see that very well, and so on and so on and so on indefinitely, so that we can get a solution that exists for all time. Right? Continuity, then in Lyapunov stability, in addition, we can get that. In this case, we just have to, so for a given desired epsilon, right, suppose that's our epsilon, desired epsilon, we just find a sublevel set which is contained in that epsilon. So there's a V of x less than gamma, where that gamma depends on epsilon, and if you stay in that, start in that that sublevel set, you'll stay in the sublevel set, so that ensures that you're in epsilon for all time. And how do we ensure that we start in that sublevel set? Well, we find the smallest or the largest ball delta, which is contained in that set. Such that v of x is less than or equal to gamma, and that's gamma of epsilon for all x, let's say, less than or equal to delta. All right. So that's the outline of the proof. Again, I'm not going to go through it. In particular, the monotone decreasing property for asymptotic stability is a little bit more complicated, so I'm not going to go over it in much detail. But that's the basic idea, right? You have an epsilon ball. You find the sublevel set within that epsilon ball, and then you find a delta in that sublevel set. So that's your delta, and that's your epsilon, and that's your associated sublevel set. Right. So that's the outline of the proofs of stability. So that's a sufficient condition, of course. So why is it necessary? So that's the important part. Here's just a couple examples we already went through in previous lecture of the Lyapunov functions for some basic systems. So here's the pendulum problem, right? This is a neutral stability problem, Lyapunov stability. So if you start in this domain D, right, we find a sublevel set which is contained in that domain. So not all of these are, but some of them are. So a sublevel set which is contained in that D. For this Lyapunov function, and we showed that the derivative is 0, so it's less than or equal to 0. And so we have the Lyapunov stability conditions, but we don't have the asymptotic ones, because this is occasionally, or always actually, equal to 0. In the mass spring, of course, we have damping, so we should be able to get something stronger. And in this case, we propose the obvious kinetic and potential energy Lyapunov function. We take its derivative, and it's less than negative cx dot squared, which is strictly less than 0 for x dot not equal to 0. So strictly less than 0. So this one proves Lyapunov stability, and this one proves asymptotic stability. This one is local, this one is global. So necessity. Well, that's an important point, and we should come back to now the interpretation of Lyapunov functions, because Lyapunov functions, right, say the converse theorem of Lyapunov says there exists a Lyapunov functions, which actually at this point shouldn't surprise us, right? Because if we go back to our optimization problem, right, so what is the secret of life, right? One metric, just one thing. You stick to that metric, and the rest doesn't mean anything, right? So in this case, what are we trying to prove, right? So if we're trying to prove that the size of the output for a given initial condition, right, is bounded, right, then it makes sense to choose our Lyapunov function to be some metric of that bound, right? So in particular, right, if we think about this statement, right, if the system satisfies this property, well, how do we prove this with the Lyapunov function? Well, we can just define our Lyapunov function to be the property that we want to examine. So, for example, if h is our metric on the signal, right, and we have a solution map, then it's obvious what our Lyapunov function is. It's just the composition of that metric with the solution map applied to the given state. Right? So in that sense, right, if the system has this property, right, we want to analyze this metric, there's always a Lyapunov function which proves it. Right? And so, for example, linear systems, we could find this explicitly. So it's explicit for linear systems, where we had, say, if we're looking at the L2 norm, right, H is the L2 norm, right, from 0 to infinity, right, and G is the e to the atx, right, then we can just compose those to get our Lyapunov function, right? V equals integral 0 to infinity of e to the atx squared dt, right? B of x, right? So in this case, we know exactly what the Lyapunov function looks like. In the nonlinear case, of course, we don't have an explicit expression for this. Right? But we know it exists, and we know that the metric exists, so we know that a Lyapunov function exists, which establishes that property, that L2 norm gain on our system. Right? So this is a very important point, right? That there always exists a Lyapunov function, which proves whatever you want it to do. It's perfectly well defined by your signal metric that you've chosen, and your solution map. So if both of those things are well posed, right, are well known, then a Lyapunov function always exists, right? And this is important because it's much easier to search for Lyapunov functions than it is to explicitly characterize the properties of the solution map, right? So in particular, we almost never can find the solution map. Because it's a very complicated function of initial condition and time in particular is very complicated. So it's almost impossible to find the explicit expression for that. But it's much easier to find a Lyapunov function. And the cost to that, of course, is the Lyapunov function only tells you one thing. It tells you about your particular metric that you've chosen. And so you sort of have this advantage that Lyapunov functions are easy to find, but the disadvantage that they only tell you the one very specific thing. But if that one thing is the only thing you care about, well then, right, the rest doesn't mean anything. In particular, when we mean the rest, we mean an explicit form for the solution map. So in practical terms, right, it's impossible to find the rest, right? So we better focus on one thing and just ignore it, right? Maybe it doesn't mean anything, but it doesn't mean anything to the particular optimization problem that we've decided to define. And when we get to part D of this lecture, we'll talk about specific problems for specific metrics. And again, just to labor home, to reiterate the linear system case, right? In this case, again, we're looking at the L2 norm of the system, right? Again, as we've defined it before, that's our H. In this case, we've got our system here, and we have actually an explicit form for the solution, so we can actually find the solution map G. For initial condition, it's this one. For an input, of course, it's the convolution integral. But we don't need to re-go over all of linear systems theory, I think. But in any case, if we have this L2 norm, and we've defined our obvious Lyapunov function, we can actually just plug in for the solution map and find our Lyapunov function. So the x0 doesn't depend on t, so we can bring it out, and then we just get this. And that, when we integrate it from 0 to infinity, comes out to just something, a matrix. Right? So in this case, of course, this was the Lyapunov function for the observability gramming, which told us something very specific. And it satisfies this very specific condition here. And of course, later on, we reduced it to a set of linear inequalities, and or a /LMI. Right? But in any case, right, in this specific case, we know what the Lyapunov function is, but we don't need to, right? We know it exists, and we know it has a quadratic form in this case, which we don't know in the nonlinear case, but we may be able to determine properties of the Lyapunov function. Okay. So let's look at then one class of Lyapunov functions which establishes a very specific property. And the specific property that we're going to focus on is that L2 gain, right? It's from initial condition to L2 gain of the solution. Right. So what is our Lyapunov function, right? So Lyapunov functions, right, basically have to satisfy a couple properties, and one of them, of course, is always positivity. Right? In this case, because we're going to be looking at the L2 gain properties, we want to actually be focusing on actually I should make it G, this size, x of t, right, integral from dt. So specifically, we're going to require our Lyapunov function to be sort of quadratic. Right? And furthermore, we're going to require our derivative to also be sort of quadratic. Right? So that v dot is less than cx squared. So again, right, these conditions are very similar to the linear case, right? And they will allow us to actually prove something very similar to the linear case, namely exponential stability, which, if you recall, is that x of t squared is less than or equal to k e to the negative gamma t x of t, or x, I should say, x naught squared. Although actually I think we dropped off the squares when we defined exponential stability. Okay. So this is a sufficient condition, and it's actually it's conservative in certain cases, right? This square. So we don't want to say this is not a necessary and sufficient condition. It's only sufficient in this case, but it does allow us to conclude exponential stability, and hence this L2 gain property of the input to output. Yeah. Now, I'm actually going to go through the proof, not in terribly great detail, but just to give you a flavor of what it's going through. And again, it's going to focus on the properties of V, right? V being our sort of norm on the solution. So what happens to V over time? And we'll actually just think about V as a function of time here, because it's implicitly a function of time once you plug in the solution. So the major theorem that we introduce here, and the major sort of mathematical machinery, and this is quite a useful theorem. I need to change my color at some point. That one's already, let's switch this one as well to pink, I guess. Right, anyway, so, right, there we go. Gronwall-Bellman is a very commonly used theorem in stability and in Lyapunov theory and all over the place, and solution maps and all sorts of things. And so it's worth going through a little bit. Basically, it's a condition on, it gives you a condition on V dot, right, which allows you to conclude various properties of the solution, in particular exponential growth or decay of the solution, right, or bound on that exponential growth or decay. In stability, we want it to be decay. In existence, we prove growth, right? But that's okay. We're not going to talk about existence. But in any case, so if you think about V of t here in terms of y of t, right, it says that if V as a function of t is less than some constant gamma, well, which could also be a function of t, plus the integral from a of t times mu times v in this case. So basically, it says that v of t doesn't grow faster than rate gamma, right? Then we can bound the v by that function there, which just drops down directly, plus this sort of convolution type integral here, Where in most cases, actually, let's just make this a constant. Make that constant. And let's make this a constant. And then we just get, right, it reduces simply to this exponential bound, right? So in this case, this might be our k, and this might be our lambda, for example. Right. So it's a very important theorem, shows up all the time. And in particular, if we have, right, an initial condition, for example, y naught for our gamma, then we can conclude that this condition implies this, right? Coupled with, so these two conditions combined imply this initial condition here. And so this actually should be y naught equals lambda. Right. So there we go. That's the Gronwall-Bellman theorem. And now we can apply this to Lyapunov functions. So in particular, we're going to show that v dot is less than some gamma of t times v of t. Or actually, well, we'll talk about it in a minute. And then we'll integrate that over time to get the conditions of the Gronwall-Bellman theorem. So if we look at the proof, right, remember what the conditions were. V dot is less than negative cx squared. And v is greater than or equal to another, I think this was, so that was c3. V is greater than c1, I think it was, x squared. And v is less upper bounded by c2 of x squared. I think those were the three. So we have a condition on the derivative, strictly decreasing. We have a condition on v, which is, so it's greater than some quadratic. And then we have a condition on v that is less than some quadratic, right? So if we think about v here, we've got a quadratic here. We have a quadratic here. C1 x squared and C2 x squared. So v lies somewhere in there. Right. And of course that v dot is less than 0. So C1 and C2 can be rather large or rather small depending on the conditions. So obviously we satisfy the conditions for existence and uniqueness because we satisfy we can satisfy the weaker conditions from the previous Lyapunov theorem, right? V dot is less than or equal to 0. Actually, in this case, strictly less than 0, and v is strictly greater than 0. Right. We actually have the upper bound here, which is also important as well, and that's stronger than the previous existence theorem, or Lyapunov theorem. Right. So now let's examine that v dot, right? So v dot, of course, is less than this condition, right? Negative cx squared. And now here we get to that, the reason we have the upper bound, right? So the upper bound says that, well, v is less than c2x squared, but that also means that negative x squared, right, if we just multiply the whole thing by a negative sign, is less than or equal to negative v over c2. Right. And so we add that condition in here, and so we get x squared is less than v over c2. And so that condition now here, if we ignore the middle part, right, just ignore the middle part, we have that v dot is less than negative c3 over c2, and so that we make that our mu. We'll actually make the whole negative part mu. And we have an initial condition that v of x of 0. We make that our lambda, right? And so we apply Gronwall-Bellman theorem to show now that establishes that an exponential bound on the growth of our v, right? And in particular, right, this is our mu, this is our lambda, and so we have that v of x of t is less than the initial v of x times this exponential decay factor e to the negative c3 over c2 times t. And then notice that's why we need the upper bound on v. So now we know that V, right, satisfies this exponential decay. And so we can actually now prove that the solution itself satisfies that same exponential decay, well, slightly modified, of course, but it's the same exponent here. So here's the lower bound condition, right? So this was this condition here. So V is less than C1x2, but we're going to invert that, show that x squared is less than or equal to V over C1, which is this right here. And then, of course, we have this condition here implies that V is less than V naught here, e to the negative C2 over t, right? That's right there. And then we keep the C1 that just goes, plots right over there. Now, we're not quite done, of course, because we want to prove this is exponentially stable. So we need to get rid of V. Again, right, we have this, this condition that V is less than C2x squared. And so we can just plug that right there. V C2 x squared, right? So that's that part, right? Comes from here. Oops. Ah. How do I undo that? Right. Maybe change my color there. Okay. So that allows us to show that the size of the system of the solution is less than that input g x naught going in, and then g of x comma t is less than or equal to C2 over C1 e to the negative C3 over C2 x naught squared. And we can just integrate that to get an L2 bound on G. Integrate that from 0 to infinity to get an L2 bound on G. Right. So you see where all three of those constants come in there to give you your sort of gain on the state, so that the norm of the state may actually increase if your Lyapunov function looks like this, right? So, so that's C2 over C1. But then it will eventually decrease down to 0. So that concludes the section where we talk about Lyapunov functions. So we've shown that Lyapunov functions allow us to characterize system properties, including Lyapunov stability, exponential stability, and asymptotic stability. We haven't talked about we briefly mentioned domain of attraction, and we haven't really mentioned invariant manifolds and other things like Lyapunov exponents and stuff like that. But we spent enough time on Lyapunov functions, and so now at this stage, when we get to part D and come back, we'll talk about how to turn the search for a Lyapunov function into an optimization problem, which allows us to represent these system properties. And we'll come back to that shortly.